Internet Protocol. So Internet Protocol present in the network layer of OSA model. So network layer is the third layer which is present between the data link layer and the transport layer. So here we are trying to see that how we are going to transfer the packet in the network layer which is connected between the two hosts, that is the sender and the receiver. So the network layer in the sender side will try to receive the data from the transport layer in terms of segments. And the network layer will try to convert the received data into packets and trying to transfer the data into down the layer of data link layers. Similarly, in the receiver end, the network layer will try to receive the data from the data link layer and convert the given data into the segments to the upper layer of the transport layer. So between the two medium, we are going to see that how the data is going to be transferred. But we have seen that how the data has been transferred in the medium in the previous session. But in this session, we are going to see that how the packets are going to be get framed. Because as the sender will be having a larger size of data, the larger size of data are being segmented into a small packets. And how these packets are going to be get identified and how we are going to give a number. That is what we are going to see in this video. So in IP, this Internet Protocol, we have in two versions. First version is nothing but IP version 4 and the next one is nothing but IP version 6. So in this presentation, we are going to see about IP version 4. So this is one of the main protocol of the given three auxiliary ones. So this IP Internet Protocol is nothing but it's going to have the three major responsibilities, which is mainly trying to do the functions like packet sizing, forwarding, and the delivery of the packet at the network layers. And the remaining three auxiliary ones are the Internet Control Message Protocol, in short we'll be calling as ICMP, which is mainly used to handle the errors which is going to occur in the network layers. And next is nothing but Internet Group Management Protocol. In short, we're going to call this as IGMP, which is mainly used for delivering the multicasting of the packet from the sender sides. And the last one is nothing but the Address Resolution Protocol. This is mainly used for mapping the addresses in the network layers. Right. So this is the given format. And here we are given the five major functions of the network layers, I mean the OSA model, but we are going to focus mainly on the network layer, wherein the IP address are present in the network layers, where we have like IGMP, ICMP, ARP, and RARP. Now let me see what is happening in the Internet Protocol. As I said, we are trying to send the information from the sender to the receivers. That is, here the sender is nothing but host A and the receiver is nothing but X, the device X. So here we have, when this device is trying to receive the data from the above transport layer, and all the received informations are converted into a small packets. So the received data are divided into 4 different packets. So all these packets have been transmitted into the medium through the first router which is connected to the station A. But from this router, we cannot have the continuous sequence of the packet. Whichever links are free, whichever router are free, all these packets are transferred in all the different directions from this connected router to all the routers which are there in the medium. So 1, 3 are traveling in one link. Similarly, the packet 4 is traveling the other link, and the packet 2 is traveling on the other links. So all the packets are being transferred in the different wide directions, and at the receiver side, all these packets have been arrived at a different time interval. For example, here as per the first packet 1 received as a first, packet 4 is received as a second, packet 3 is received as a third, and packet 2 is received as a fourth. So here all the packets have been arrived at the different time interval, but in the receiver side we have to rearrange all the incoming packets, and once after rearranging only we are going to transfer all the packets to the upper layer of the transport layers. Right. So this is the format for the datagram. So whenever you're going to send a packet, so we should have the complete information about the packet. So in this packet, we're going to have the complete details about the data transfer from the source to the destinations. So now in this versions, we're talking about the version 4. Okay, so let me see what are the descriptions are given inside this packet. So VER stands for the versions. So here in this topic we're talking about a version 4. So here it is given in terms of 4 bits. So 4 bit in the sense 8, 4, 2, 1 combinations. So we are going to define that this is a 4 bits. So how can this can be represented in terms of binary number 0, 1, 0, 0. So we are going to give the identification that this is a version 4 in terms of 4 bits. Second is nothing but it's like my H len, which means header length. This is also of the size of 4 bits. Next is followed by a service type, which is of 8 bits. And next is nothing but total length is nothing but 16 bits. You just add all those bits together. 16 plus 8 is going to be around 24. 24 plus 8, 28. 28 plus 4, 32. So the total size of your datagram is nothing but the 32 bits. The total size of a datagram is nothing but 32 bits. So we are going to divide this into the header and the data. Okay, so the header is going to contain the size of around 20 to 60 bytes, and rest all the information are going to be by the data. So if I see the total size, then we're going to have the total size as well, starting from minimum of 20 with the maximum of 65,000, so 536 bytes we are going to occupy. Okay, now we're going to see in detail about all these internal functions one by one. Okay, so here I've given this small description about all the major functions which is going to take place inside our data packets, right? Let me see one by one. First, we'll start with the versions. So this VER stands for version. Since we're talking in this topic about a version 4, so we're going to denote that version in terms of 4 bits. As I said, we're going to have in terms of like 8, 4, 2, 1 combination. Since this is a 4 value, we're going to have the binary value as 0, 1, 0, 0. If it is a version 6, so with 6 is nothing but we're going to represent the numbers like a 4 plus 2 combinations. That's 4 plus 2 is something but 6. So 0, 1, 1 and 0. So that is the binary number which is represented in time the version. So if it is a version 4, if it is a version 6, we are going to represent that corresponding numbers in terms of a decimal number or a binary number. Right. So now we are going to talk about the header length. Second is nothing but your header length. So the header length in short, which has been given as a H len. So this is also of the size of 4 bit. What this header is going to do? So this is a 4-bit header length mainly defines the total length of the datagram. Datagram is nothing but the total packets. Okay, the total complete information about the packets. So it is going to define the total length of the datagram header in 4 bytes. In 4 byte words. In the top they are given that this is the total length of the datagram. Here they mentioned this is the arrow mark. This is the total length of the datagram, which of the size of 4 word. Okay, so this IPv4 datagram has a variable length header also. So this header may be changed. So here they given that this is the total height of the header. So in this header, we're going to have the complete information about what is the version, data size, and your flags, fragmentations up to source address, destination, and options. This is the complete size of the header, and this is the complete size of the datagram. Datagrams are the complete packets. Okay, so we are going to define that what is the starting and what is the starting and the ending bytes of the headers. Okay, that is what we are going to see over here. Right. First, we'll see that what is the byte can be. Okay, so first thing is that since we are talking about a version 4, okay, we are talking about a version 4 here. If suppose, for example, I'm going to take the header length as a 5. Okay, I'm going to take the header length as a 5. So here they were denoted in terms of a decimal value. This can also be represented in terms of the binary values also. If it is a binary value, I'm going to have the values like a 0, 1, 0, 1 combinations. So decimal value is something but 5. If it is a binary value, then I'm going to have the value as a 0, 1, 0, 1 combinations now. Okay, now we are going to define that what is the size of the header length now. Okay, so here I given the word as a header length as a 5. So which means that the header value is about 5 words. And what is the byte length they've given for the datagram? They've given the datagram size as a 4 bytes. Okay, so what we're going to do is now, here they're given us a 5 words. Okay, so we are going to multiply these words into the actual size of your datagram. So actual size of a datagram is something about 4 words. Okay, so we are going to multiply the header length of 5 into the 4 of your datagram. So 5 into 4 is equal to 20 bytes. So the header starting size value is supposed to be of 20 bytes. Okay, and now we are going to have the maximum values also. For example, the previous example, we have taken the header length value as a 5. But what is the size of your header length? It is of a 4 bits combination, like a 8, 4, 2, 1 combination. If I add all the values of 8 plus 4 plus 2 plus 1, which is nothing but the value of 15. So I've given the maximum value also of the respective header length value is 15. So this is either represented in terms of decimal or in terms of binary values. Okay, in this two way we are going to represent these values now. If suppose the given header length is something but 15 means, then we are going to multiply the header length into the actual length of the words. So 15 into 4 is nothing but 60 bytes. What is the previous example you have taken? 5. So 5 into 4 is something about 20 bytes. And if I take the examples as a 15 with the maximum value, so 15 into 4 is equal to 60 bytes. So always in the IPv4, we are going to have the header size as minimum value which starts with the 20 and the maximum value we are going to have it as a 60 bytes. So totally the header length sizes falls between 20 to 60 bytes. Why they are saying as a 20 bytes? For example, if whenever you're going to send any postal or if you want to send a resume to any of the companies, or if you want to send any greeting card to any of your friends, what are you doing? You'll be writing what is the send receiver address, like the name, door number, street number, area name, district name, as a state name, and the pin code and your phone number. Everything you're going to give a very clear information. Yes or no? So we know very well that for transfer, wherever you're going to send any data, we should have this as the clear address, like door number, street number, area name, district name, state name, city name, everything you're going to specify very clearly. If any one of the information is going to become less, what happens? This respective greeting card or the resume is not delivered to the respective company or your friend. Okay, so we were going to define the minimum value of your address. Okay, the minimum value of your address is supposed to be of 20 bytes. If it is less than 20 bytes, then this information will not give a clear information to the receiver. So who are going to be the mediator? Like for example, if the postman is going to receive the respective greeting card, by seeing the address, the postman will not have a clear idea about the respective addresses. So he may have some confusions. So in order to avoid that only, we are supposed to clearly define what is the addresses. So if your address size is very, very less in number, then you're supposed to make some extra bits to add it to the original information so that you can bring the size of your header with the minimum length value starting as a 20. If the header value is less than 20 bytes, then you're supposed to go for some padding. You're supposed to go for some padding. For example, if I have 15 as your header length, I mean, if it is less than that, then what if they're given the minimum length as here as a 5? If I have like a 1, 2, 3 or 4, if that is the case, if I have the header length as a 4, what happened? 4 into 4, 16 bytes. What should be supposed to be minimum size? 20. But I got only 16. Then 4 more bytes supposed to be get added. Added in the sense we are going to do some padding concept so that we are going to have the minimum size of your header as a 20 bytes. Okay. Right. Now we are moving on to the service type. The service type is the size of around 8 bits. Okay. Which has been the third locations of after the header length. And this is mainly used to differentiate the service types. That is mainly to define the classes of the datagram for the quality of service. For example, quality of service in the sense, we are going to define about the minimum delay, the maximum throughput, maximum reliability, and the minimum cost. But we're not going to focus about majorly about this. And sometimes this service type could also be defined with the help of the optional values. Okay, this optional values in the sense extra information only. This is mainly used to for testing as well as a debugging purpose, and the size of your options can be maximum of 40 bytes long. This is mainly used for testing as well as debugging process. And next we're moving on to the total length. So where is the total length? That is after your differentiated services. So this is of around 16 bytes. Sorry, 16 bits. Now we know that this is the header. Header value starts with the value of 20 to 60 bytes. This is of header. And we're going to define what is the total length of your data word. Data word is datagrams total size is something about 4 byte word. With this, we're going to define what is our actual size of the total length. Okay, so this is of 16 values. So we are defining the values or in terms of binaries only. So 2 power 16 minus 1, because we are going to have the starting value as only 0. So we are taking as a minus 1 values. So 2 power 16 minus 1. So we are going to have like a 65,536 minus 1. So I'm going to have as a 65,535 bytes. So these many number of bytes can be occupied in the datagram to transfer the information from the source host to the destination host. But rarely we are going to use maximum only 1,500 bytes out of this is 65,000 cases. Okay, let me see. Right. So this 16 bits, which is going to define the total length of the header. Header plus data. So what happens? Whenever are going to define the datagram is nothing but the addition of the header, and the total size of your length. So that includes the datagram. Okay, so these with the 16 bit of your datagram length, we are going to have the total length of the data word at the maximum of 65,535. When I want to define the data length, so what is the formula then we are going to use? Length of the data is equal to total length. What is the total length I'm going to have? That the power, okay, minus header length into 4. Total length is nothing but this is your actual length minus header length is nothing but this given data into 4 we are going to have, because why I'm using 4 is nothing but the actual size of your data word. Okay. So the payload in the Ethernet varies from 46 to 1500 bytes. So here also we are going to have the minimum condition as whenever you're going to transfer any data in the Ethernet cable, we should have the minimum value of the byte data payload value as a 46 byte, and maximum you can have around 1500 bytes. For example, if the size of a datagram is less than 46 bytes, okay, some padding will be added to meet this requirement. In this cases, when the machine decapsulates the datagram, it needs to check the total length defined to determine how much is really data and how much is padding. For example, what I said for the header, we should have minimum as 20 bytes. Similarly, for the payload in the Ethernet also, you should have minimum value as 46 bytes as your payload values. But if you're going to have less than the data size from the sender side, means what you're going to do, you're going to add some information extra to the original value. For example, we are going to have your bytes, bit values. With the addition to that, we are going to have some addition of a byte. We are going to call the process as a padding process. Okay, so what is the real data and what is your real data we're going to have. So we will be adding all put together. We're going to have the minimum value size of your value is about 46 byte. We are transmitted through the medium, and in the receiver side, we know that what is the size of your actual data and what is your real data. So we are going to segregate the data, the real data into separations. Then we're going to consider only the real data here. Okay, so this padding will be removed in the receiver side as a decapsulation process. Right. Next, we're moving on to the fragmentation process. What is this fragmentation? So under fragmentations, we're going to have like 3 main classifications like identification, flags, and the fragmentation offsets. So what does this identification means? So this identifies a datagram originating from the source. When a datagram is fragmented, the value of the ID field is copied into all the fragments, and this helps the reassembly process at the destination site. Okay, I'll give a small example for identification of this entire process. For example, whenever you're going to travel from one location to one country to the other country, for example, you may be living in India. So whenever you're going to travel from India to some other country of Norway or California somewhere for a 1 month of vacation trip you're going for, since you're going to stay for a 1 month of time period along with your family all going, so there were around 4 members in your family, like your father, mother, and the two children are totally taking up. So what you'll be doing then, since you're going to stay for a 1 month of a period, 4 family members were there. One luggage bag you will not be taking up. You'll be taking minimum of 3 bags. Yes or no? One for the first child, second for the third child, second child, and the rest are for the family members. So totally you'll be having like minimum 3 luggages you'll be having. Yes or no? Since you're starting from India, so you'll be giving in the suitcase that what is your source address. That is, this luggage is belonging to whom. So because you're the owner, so you're going to stick out your name and the addresses in the respective all the luggages. So you'll be having like 3 luggages. So luggage 1, luggage 2, luggage 3. You are going to mention the same addresses in all the 3 different luggages. Yes or no? So you have a larger size of a data. The larger size of a data cannot be occupied in a single bag. So you're trying to divide the larger size of a data into small luggages, luggage 1, luggage 2, and luggage 3. And in all the 3 luggages, you're going to stick your source address. Source address in the sense your own address, the owner address of the luggages. And this has been, after checking what you're going to do, this has been given to the luggage area now. So they will be taking to the luggage through the trolley and then taken to the flights. So again, from the flight, it has been taken to the respective destination area also. Again, the destination area, this luggage, because in the flight, all the passengers' luggages are been taken, put together. And sometimes all the suitcase also will be same in color, same in size. So you may have some confusions also. So whenever the luggage are going to come in the trolley, you will keep on watching. If you identify that same color of a suitcase or same size of a luggage, you'll be having some confusions, yes or no? So by seeing your addresses, the label on the respective luggages, you'll be rearranging all that, like luggage 1, luggage 2, and luggage 3. Yes or no? So the larger size of data are divided into 3 luggages in the sender side. Whereas in the receiver side, what happens, you'll be receiving all the data put together, but at the destination side, by seeing the addresses, because all the 3 luggages are belonging to a single family only. All this in all the suitcases, you can see that the same addresses have been stacked. Yes or no? So you're going to rearrange all that in the receiver sides. That is what the point they mentioned here as a datagram originating from the source host. When a datagram is fragmented, that means it is all divided into small pieces. The value of the ID field is copied into all the fragments. What is that ID? Your source ID, your home address. Your home address being sticked onto all the fragments. This helps the reassembly process at the destination host. Next is talking about the flag field. In the flag field, we are going to have around 3 bit of fields. And the first bit which has been reserved, and second bit which is used for the command of do not fragment, and the third bit is nothing but more fragments. And if the value of 1 is going to be present in that value. So we are going to have like a 3 bits of value. 1 has been reserved. So 1 is not been used for almost. So second bit and the third bit are been used. Now D stands for do not fragment and M stands for more fragment. So we are going to see that if the value of D is 0 or 1. So if the value of M is nothing but 0 or 1, what will happen? Okay. Next is something called fragmentation offset. This fragmentation offset is around a 13-bit field, which shows the relative position of this fragment with respect to the whole datagram. Okay, we are going to define about the position of the fragment from the whole datagram. It is the offset of the datagram in the original datagram, which is measured in terms of 8. So we are going to divide all your fragments in terms of 8 bits. Okay. First, we will start with the fragmentation process. As I said, from your side, you're going to have the largest size of your luggage. That largest size of luggages are being transferred from the India to Norway countries. Yes or no? So all the we cannot transfer as data as a single bags. So what we're going to do, we're going to divide that size of a 4000 bytes into a smaller segments. So in that suitcase, you're going to define the address of the source. Yes or no? So for that, we're going to allot some spaces for the header with the size value minimum of 20 bytes. So out of this 4000, 20 bytes are being taken for the header. What is the remaining left out values is nothing but 3980 bytes are being left out, which is being used for luggages, which is used to place your luggages inside your suitcase. So inside your suitcases, 20 bytes which are allotted for giving your address name, and remaining 3980 bytes have been allotted for carrying your load, that is your payloads. And now what we're going to do, we know that the Ethernet frame maximum we can able to occupy only 1500 bytes. But what is the actual size? It is around like a 3980. But what is the actual size of the frame which is occupied in an Ethernet? Only 1500 bytes. Now what we are going to do is, we are going to divide this 3980 bytes into the maximum 3 segments. Because this 3 segments, we can have a maximum of 1500. So we're going to divide this in equal numbers like 1400, 1400 and 1180. If I just add all these values to put together, we just see that 1400 is something but 2800, and rest of which is added with the 1180. So we're going to have the max, the original value is 3980. So we are trying to divide the luggages in equal values. If I had here like 1500, 1000, then you will be having like more luggages, then you can able to carry you more weights. So we're trying to divide the value in terms of like equal values, and we're giving the name as IP1, IP2 and IP3. So IP1 with the maximum of 1400 bytes, IP2 with the maximum of 1400 bytes, the IP3 with the maximum of 1180. So what is the actual size of your luggage? The bytes, 4000 bytes. We have divided that into a header as a 20 bytes. The remaining data is going to be occupied with the size of around 3980, and this 3980 are being divided into 3 different luggages. That is your 3 different IP addresses. Now this is what we are going to transfer from the source host to the destination host. Right. Now what we're going to do is that next we will have to identify that. Yes or no? As I said, the example, like if all the suitcases like are the same in color, or if it is in same in size, and how to differentiate that. So we have to be very clear with that. Yes or no? So by sticking your address with the same address in all the suitcases only, you can be able to identify that very clearly. Yes or no? So in the identifier, we are going to have the X as your address. The same X address supposed to be replicated in all the IP packets. IP packet sense all your IP packets, we are going to give the same identifier as X, X, as plus X. By seeing the same addresses in all the 3 different suitcases, we are going to receive that in the destination sites. Yes or no? So what I said, so in the source and in the receiver side, we are going to replicate the same address in all the luggages. So we are going to have the X plus 1. So in the sender, we are going to have only as X. Yes or no? From the home, you're going to have as a single luggages only. But when you're going to travel, what happens? We are dividing that 4000 into 3 different luggages. But all the 3 different luggages are belonging to the same family only. So you're going to divide the value as XXX in all the IP addresses. Right. Next is the flag, as I mentioned. Flag is of 3 bits. In the 3 bits, 1 bit which is used for reserve, and remaining 2 bits only are being used. That is a D and M. So here the D stands for do not fragments. Okay. If the value of a D is nothing but 0, then what does it mean? Since the value of a D is nothing but 0, what is the name of this? Do not fragment. If the D value is going to be 0, which means that then I'm going to do the fragmentation. Actual name is do not fragment. If the value is 0, is within the opposite manner only. So I'm going to divide the incoming data into a small segments. So we're going to call that as a fragmentation. If the value of your D is equal to 1, so do not fragments, I should not, when the value is high, then I should not supposed to do the process. So I'm not going to do the fragmentation process because the size of your original luggage is very, very smaller. So there is no need to divide a larger size, a smaller size of luggage into again a smaller sizes, because the minimum size of Ethernet data we have given as 1500 bytes. But here the IP address datagram is nothing but less than 1500 bytes. In that cases, we are not required to divide your IP datagram into fragmentations, right? And next, we are going to move on to the M. M stands for more fragment. What's D? D is nothing but do not fragment. It's not supposed to break your fragments. Now, if I have larger size of data, in that cases, if I have the value of M is equal to 0, means when, what I'm going to do is now, if it is a M value is equal to 0, this is the last frame or this is the only frame. Which means that the actual size of data is about 1500 bytes. So no need to divide it. But if the size of a packet is going to be more than 1500 bytes, in that cases, I'm going to divide your incoming datagram into a fragmentation process. So this is not a last segment. There are segments which is coming in the queue. That is IP1, IP2 as well as IP3. And next is talking about the fragmentation offsets. Okay, as a sets. These are the previous points we discussed, that is the actual size of a data into a header into a data size and dividing into 3 different IP addresses with the same identifiers. And also we have seen that what is a flag like do not fragment as well as a more fragment. So all this IP1, IP2, IP3 are nothing but belonging to a single IP address only. Right. Next is fragmentation offsets. What is this? So we need to find what is the offset between every bytes. Okay, so what is the actual size of the data? We have around 3980. This is the actual size of a data, and we're going to divide the numbers in terms of 8 bits values. So we're going to divide the actual values with every 8. So first offset, we're going to find the values with the actual number. We have divided this into 3 different segments. Yes or no? What is the first segment? Maximum byte we have allotted 1400 bytes. So this 1400 bytes is allotted for the first one, and the second 1500 is allotted for the second one, and the remaining is something but 1180 is allotted for the last one. So we're going to have the keep on the addition of your values now. So first byte starts with 0000 up to the maximum of 1399, which means that starting from 0, so we take only 1399 values here. So dividing the maximum value of the first fragmentation value by 8. So 0 divided by 8 is value is going to be 0. So the offset value for the first set is nothing but 0. And we're going to define what is my second value here. So second value is nothing but I'm going to add this minimum value. What is this maximum value here? 1400. So this is 1400 value divided by 8 is equal to 175. So the offset value for a second is nothing but 175. And third one is nothing but 1400. 1400 put together something but 2800 divided by 8 is nothing but 350. So we're going to have the offset value for the last one is nothing but 350. So here I am going to have only 0. This is the starting value something but 1400, and this starting value something but 1400 plus 1400 is something but 2800 here. So the first, second as well as the third. For the first one, we're going to have as a 0. For the second one, we're going to have as a 175. And third one, we're going to have like a 350. Right. So what we are doing actually here in this fragmentation process. A datagram can be fragmented by the source host or any router in the patch. So what we can do, the fragmentations can be done by the source or by the router. For example, from the home, you have taken the all the luggages putting into a single luggages. But when you're coming into the airport, by seeing the security, what they'll be so sorry, sir, we cannot take this such a larger size of luggages. Please try to segregate your larger size into smaller pieces. So the dividing of your original size of a datagram into smaller fragmentations can also be done by the router. Router in the sense, because we are going to travel through the n number of routers from the source to the destinations. So during the medium, we'll be having the router also. So router also have the rights to divide the larger size of a data into a smaller size of your fragments. Okay, because once we are going to divide all, they will be having smaller fragmentation, more fragmentations in number. And while traveling through the n number of mediums, we will be receiving a different time at the destination. So we have to reassemble all the data. Whenever you're going to for a fragmentation of a process, we should have a equal identifier. That's very important. Yes or no? Right. So whereas a fragmented datagram can travel through the different routes, and we can never control or guarantee which route a fragmented datagram may take. Yes or no? So as we seen in the previous examples also, we have seen like 4 different packets. All these 4 different packets are traveling in a different route. We doesn't know through which route the packet may be travel. In the destination level, we will be waiting for receiving of the packets. Yes or no? So we cannot guarantee for the data, and we cannot say that in which route it is being traveling up. So all the fragments belonging to the same datagram, yes, should arrive at the destination host. So it is logical to do the reassembly at the final destination. So what we have to do, in the receiver side, we will be doing reassembly process, because all the packets are traveling in different routes, so may arrive at the destination in different time periods. We'll be having only the incoming, like a shuffling of the order. We have to do the we have to arrange all the data in the sequencing of the numbers. So here this is an example. So for example, like we have like a fragment 1, fragment 2, and fragment 3. We have the original size of a data diagram, and this original size of datagrams are divided into 3 different fragments like F1, F2, and F3. So F1 and F3 are taking in one route from the router 1 and router 2, and the F2 fragments are being divided again into 2 pieces by the router. Yes, so router also have the rights to divide the fragments. So the fragment 2 is being divided into another 2 pieces like F.2.1, F.2.2. So this router 2 is taking place, router 1 is transferring the data into the other router directions, and that is all traveling in the other link. See in the receiver side, F1, F3, F2.1, F2.2. So what the receiver have to do, we have to do the reassembly process like F1, F2 as plus F3. So we have to do the reassembly process in the destination side. So what's the point we have to know here? That the objective here is something but the source and the router have the rights to do the fragmentations of the incoming datagram. Right. So here the fragmentation example has been given here. Here the byte size value is something but 0 to 3999. So this is the original size of the datagram. We are trying to divide that into 3 different values, as it's been like 1400, 1400, and the last value. So we are trying to divide into 3 different fragments. The 4000 byte values have been divided into 3 different fragments, like 1400 values with the 2800. From 2800 into the maximum of 1000, 4000. Yes or no? So this is fragment 1, fragment 2, and fragment 3. So we are trying to divide the second fragment into another 2 pieces of a fragment, as we seen in the previous example, like F.2.1 and F.2.2. Yes or no? So we are trying to divide the values into another 2 pieces of the respective fragments also. Right. Next is nothing but a time to live. What is time to live? As we've seen the examples in the message switching in the unit 1 topic, the previous topic, like whenever we are trying to transfer data from the mobile phone or from any other devices to the receiver, so every data will be having some lifetime. Without lifetime, the data cannot be traveled. Yes or no? For example, I'm trying to send a message now that tomorrow you'll be having your classes. By tomorrow, 9 a.m. you'll be having your classes. This is a common information without any clear that what is the date. I didn't specify any date yet. Tomorrow you'll be having your classes by 9 a.m. But I have transferred this data at one date. But you'll be receiving this information after 3 days. Then what does it mean? You may think of that whenever the date you have received, from the day, okay, tomorrow will be my classes. But you have skipped the classes. So the data information supposed to be have some deadline time period, so that within that stipulated time period, the data is supposed to reach the destination. So without lifetime, a packet cannot travel in the medium. Right. So first, what we're going to do, whenever a data is being started from the source host. So whenever the source is going to start deliver the packets from the sender side, we should have some number of hopping. That is how many number of lifetime. That is, for example, here they given the lifetime value as some x. I'll be taking this x value as some 5 here. For example, I'm taking now. So whenever the source is trying to send the packet from the source to the nearby router, okay. So what I'm going to do in that case is the system I'll be taking as a source, and I'll be transferring the packets to the nearby first router. Okay, I'll be transferring my IP packets to the nearby first router. Once this router have received the data, means I have to minus this value as x minus 1. That is 5 minus 1. So what is the next number of hopping can take place? Only 4 in number. So actual size is different, time is different by 5. So 5 number of times can able to travel from the source to the destination. Okay, so now it has received it to the first router, so I've taken the x minus 1. So that is 5 minus 1, I'll be having the value as 4 now. Now this router will be transferring the data to the another router. So like I said, we keep on transferring, we keep on minus. So what happened now? X minus 1, x minus 1, x minus 1. Keep on when we're doing minus 1, at one particular time period, you'll be having the value as a 0. What happened? Now one of the router have received the value as 0 from the incoming packets. Okay, so again I cannot minus this value with 0 minus 1. Okay, so what this router will do now? No, I have received the value as a 0. The lifetime of the respective packet is been over. So try to resend the packet. I cannot forward this packet to the next router. So this router has the rights to discard the incoming packets, because the lifetime for the respective packet, the values become 0. So another time, this router will not transfer packets. So what happened? Once the router received the values as 0, then it will not transfer the data to the another router. So it is informing the sender again to transfer the data with another lifetime time period from the source to the destination. So this is the time to live, how long the packet can stay in the medium between the two hosts. So this is a time to live. In short, we're going to call this process as a TTL. Okay. So that's what explanation I've given over here. Right. So this is the another example I've given. So here what happens is that the source host A is trying to send with the data of 255. Okay, so 255, what is the router will do? Minus 1, minus 1, minus 1, minus 1, we're doing here. So the source host has given the hopping number as 255. So the router 1 receives the incoming packets. So the 255 minus 1, the output is 254. Yes. So this is transferred to the next router. Next router received with the value of 254. So 254 minus 1 is the number 253. Like as minus 1. So this host has received with the value of 252. So finally, with some number of hosts, the host B has received the data, it has been accepted. So when this router 3 is receiving with the incoming host value, hopping value as 0, means this router 3 will not deliver the packets to the host B. It will discard the data and it will pass on the information through the router 2, router 1, and then to the host B again to retransmit the data. Okay, this is the time to live process. Okay, so now we'll have a small recap about the entire process what we have seen. What is IHL is nothing but the header length with the size of 4 bits, and next total length is nothing but with the size of 16 bits, and next is datagram, which mainly is used for identification process and to do the reassembly process in the destination side. So we'll be having encapsulation in the sender, decapsulations in the receiver side period, and next is fragmentation words. This is mainly used for pointing the offset values between the two positions. And your DF is nothing but do not fragment, and MF is nothing but more fragments. The values can be either in terms of zeros or 1. And next is time to live is nothing but to control the number of hops between the sender as well as the receivers. Now we are moving on to the next field called as a protocol. Okay, yes. What is this protocol here? So we have seen some numbers in the beginning of the slide, like internet protocol, like a control message, management protocol, or some RSP, yes or no? So we have seen like 3 different types of protocols. So whenever the data have been originated from the source, they might have prepared the data in some format with some support. For example, if I know since my mother tongue is going to be Tamil, then I'll be preparing the language in terms of some Tamil script, because I know that is a familiar language. But I'll be converting the Tamil language into some English language with some other transmissions now. Since I'm going to use a common platform for my data transmission, I should use only as English. That is a common platform. So I'll be converting my English or the Tamil language, that is the original language, into an English, and this English words are being transferred through the medium, delivered to the receiver. Receiver will be receiving the incoming message in terms of English and try to convert the message into their own language. So their language can be a Telugu, their language can be in a Hindi. So again, the translation should be text based. Yes or no? So what are the protocol they are trying to do? That protocol number are supposed to be specified in the protocol field. So they can use any type of protocol which can be decided by the sender and the receiver. Most probably what are the protocol we are going to follow in the sender, the same protocols should be followed in the receiver side also. Okay, so this field defines the higher level protocol, that is a transport layer that uses the service of the IP. So here what we're going to do is that we're going to do the encapsulation from the higher level, because from the higher level in the sense above network layer will be having a transport layer. So from the transport layer we're going to define that which type of protocol that we are going to use. If I'm going to use TCP protocol, that is a transmission control protocol, means then I should use the service protocol field number as a 6. If I'm going to use the UDP protocol, then I'm going to use the number as a 17. If it is ICMP, I'll be using the number as 1. IGMP means 2. OSPF means the number I'm going to use it as a 18. So now see here, now inside the network layer, I'm going to do the encapsulation process. Okay, I have a data and followed by the payload. Data's header size supposed to be 20 to 60 bytes, and remaining all is all occupied by the payload. So inside the payload, I'm going to have the data. The data are given in some specified format. Whichever format I'm going to use, with that respective number have been specified inside the respective protocol field. If I'm going to use TCP, then I should use the number as a 6. If I'm going to use the protocol as a OSPF, then the 89 is the number which is specified inside the protocol field. So that respective number has been specified inside the respective protocol fields. Right. And next is nothing but header checksum. What is this header checksum is nothing but. For example, previously when we are talking about this error correction and detections checksum process, we are trying to do this. So checksum is nothing but whenever the data has been transferred from the sender side, we'll be trying to transfer the data through the medium. But in the medium, the data may be corrupted by external disturbance. So it may change the value, actual value of a data into some other value. When the receiver receives the data, we will not receive the correct data which is sent by the sender. So your data has been corrupted. So, in the similar way, whenever we are going to transfer the original information, we won't focus only on the data. We should suppose to focus on the datagram header also, because your header followed by your data. So, error checking is supposed to be done in the datagram header also. Okay. We have to do that in the datagram also. That is what the point we're going to say is IP is not a reliable protocol. It does not check whether the payload carried by the datagram is corrupted during the transmission or not. So it doesn't know that. So datagram header is added by the IP. Datagram header is added by the IP, and its error checking is the responsibilities of the IP only. What they're saying, the datagram header is added by an IP, and its error checking is the responsibility of the IP only. So they're giving a blaming on the IP only. Yes or no? So errors in the IP header can be disaster. So we are not supposed to focus only on the payload, that is original data. We're supposed to focus on the datagram, or that is a header also. For example, inside the envelope you have your resume and sending your addresses to the respective company, but during the transmission of a postal envelope cover, a drop of water which is falling on your address and your data has been erased by mistake. You just imagine that the postal man cannot able to read the exact address. So your resumes will now be delivered to the respective company. Yes or no? So we have to give importance to the sender address also, the receiver address also, so that the respective content, that is the datagram, will be delivered to the receiver. So we are not supposed to focus only on the payload, we are supposed to focus on the datagram header also. For example, if the destination IP address is correct, as example I said, if suppose during a postal transmission, if your data has been erased or by mistakenly somebody scribbled on the top of the address, means what happened? It won't go to the respective host. It will go to somebody a wrong host. If I'm going to do some recorrections, it will go to the wrong host. If the protocol field is only corrupted, the payload will be delivered, but the protocol will be wrong. What they're saying, what is this protocol field? We have seen like a UDP, you have seen like a IGMPS and all that. If suppose there if I'm going to have a wrong information in the protocol, it will go to the wrong protocol in the receiver sites. So we should suppose to focus on the destination address, protocol field, and the fragmentation process. If the fragmentation is being corrupted, what happened? We cannot do the reassembly in the receiver sites. Okay, so in any area, if in any field, that is the IP address or the source address or the protocol field or the fragmentation process, anywhere if the bit value is going to be get changed from 0 to 1 as well as 1 to 0, then we cannot able to recover your data in the receiver sites. So for those reasons only, what we're going to do here, the IP adds a header checksum field also to check whether the header and not the payload. So because if the address becomes wrong, what happens? The respective data will not be delivered to the respective destinations. And last is going to be your source and the destination address. So source address and the destination address also should be specified in the given datagram. If suppose you have given only the receiver address, it will go to the respective destination if it is perfect. But what happens if suppose the receiver is not present over there? What happens? The postal address will be again sent back to the sender address also. So we should give the source address as well as the destination address in the respective datagram, which is also of the size of 32 bits. So the source and the destination address format now. A datagram can have up to maximum of 40 bytes of the options. Yes, as we have seen in the last point, right? It can be used for mainly testing as well as debugging process. Yes. So options can be used that is for mainly network testing as well as debugging process. Options which are mainly or not required a part of the IP header, but options processing mainly which is used for only IP softwares. Mainly this is not used for your IP header process, but this options field can be used mainly for the IP software purpose only. So all implementation must be able to handle your options if they are present in the header only. Okay, so mainly this is used only for the software purpose, not for the header process. Okay, and last is your payload. So payload is going to be the bottom of your IPv4 structure. What we're going to have inside your data? We're going to have a transport layer segment ICMP messages. So this is the data where we're going to have the original information which has been sent by the sender. But before that, what we do, we see what is the source address, what is the destination address, what is the checksum, what is the flag field, what is the fragmentation. All these things are being done to safeguard the data which is generated by the sender. We have to deliver this data to the destination. For this, only we have seen all the fields in the front. Okay, right. Now we have seen the data. Now we are transferring all the data, but we have to give some security also for this data. Yes or no? Because now in this present situations, all the informations are passing only to the internet. 10 years back and all, 50% we are working on the internet, 50% we are working on some other off the internet. But nowadays, every process in the real world are happening only with the help of internet. For example, all the online classes are being taking place only through the internet. Without internet, nothing can be take place, because if there is no internet, half of the worlds have been died. So we have to give more security when we want to transfer data, because all the informations are transferring through the internet, which is beyond the world. We cannot justify, we cannot think of that what is happening in the world inside the medium. So some intruder may try to see what is the data which you have sent. For example, some of your friend may know your mobile phone password. Sometimes they might have noticed. In that cases, when they're going to take your phone, they may type your password and they can log in and see what is there inside your phone. Yes or no? So nearby also can able to see. But what the third party persons, they try to do like, for example, we all know what is a mobile phone password. Maximum we can have only 4-digit numbers. What is the number we have? Starting from 0000. Then we're going to have like a maximum 9999. I'm going to have. So 00000 up to 9999. I'm going to have the numbers. So within this, one day you're going to try the 3 passwords. So one day 3 password, 3 password, 3 password, 3 password. You'll be keep on doing at one time period. You'll be getting the passwords. So likewise, the intruder may try to get your password, get your data, change your data, anything they can do it. Okay. So now we have to give the security for your data when transferring between the host to sender to the receiver. First point we're going to see about the packet sniffing. What does packet sniffing means? So the intruder in the sense some X person who is present between the two hosts, that is in the medium is present. They are going to make a copy of your data. For example, you're trying to send like your PIN number, right? You're transferring a PIN number from one phone to the other phone. What happens? You're sending some PIN number. This PIN number may be seen by the intruder and they may have a copy of that. But as a sender doesn't know that somebody might have copied the PIN number. Yes or no? We're going to call this process as a passive attack. Passive attack in the sense where either the sender or the receiver doesn't know that this data may be copied from by some X person in the medium. So this does not going to change any of your data what have been transferred from the sender to the receivers, and it is very difficult to find the intruder who is present in the medium. Okay, but we can stop this process only by doing your encryption techniques. We have to do some algorithm. By doing some algorithm, we cannot able to find what is the data you have generated. As I given the clue that if I'm going to send a password like a 2-digit number, so what is the 2-digit number I have? Like a 0 to 99 I have it. So with this you can able to trace it. Yes or no? But you should do some algorithm technique. So this given original password should be processed through your algorithm and I'm going to get some new value. That new value has been transferred through the medium. So by seeing this value by the intruder in the medium, he doesn't know that what is this value it is. He could not able to convert in which formula he has generated this data. You might have seen in all your WhatsApp that in the top like encryption word in your WhatsApp text messages. Yes or no? Which means that with the 256 encryption they have mentioned the value with the bit size. Which means that they have done some algorithm with the maximum value of 256 bit by converting like 1 to A to B, B to C, like 1 to 0, 1 to hexadecimal, like this, doing some number of a process, converting original message into some other manner of messages. Okay, so what happened? An intruder was going to present between the two and going to get your original data. Right. Third one is something about the packet modifications. So what this intruder is going to do now? He is going to take your information and is going to change the content. For example, you are sending you are sending like a 10,000 rupees of a cash. I mean 10,000 rupees you're going to transfer money from the sender to the receiver, but what the intruder will try to do, they will change, removing one of the value of a 0. Yes or no? And only 1,000 rupees is going to send back to the destination. Remaining value is taken by the intruder. So they're trying to change, modify your data. For example, you're trying to send the value as an apple as a text. Okay? And this apple word, this A value can be changed into some L. What happened? The meaning is completely changed. So what the intruder will do now is trying to change the content which is generated by the sender. Okay, so the receiver will try to receive the data, and the receiver also may think of that, okay, this is the actual data, okay, let me accept this as the original data. But the receiver doesn't know that whether this data has been modified by the intruder or not. So what we have to do here, we have to incorporate some data integrity mechanisms in the medium sites. Okay, so before opening in the receiver side, the receiver have to do the process of the data integrity. After the process only, he is supposed to open the respective packet and have to check the respective information sent by the sender. Okay. And last is nothing but IP spoofing. Okay. Which is nothing but a masquerade functions. Which means that some third party is present inside the medium, but nobody knows. Yes or no? That is one case we have seen. Nobody knows. The sense in the previous cases like in the intruder is present in the medium, but the sender and the receiver doesn't know. Whereas now what happens here? As like you, okay, as like you, the person is going to act. For example, I'm going to transfer the information from U to V. Okay, I'm going to transfer the information from U to V. But what happened? Instead of this U, the attacker A is going to act as a U. So, as like a user U, attacker A is going to act. He is trying to send the information to the victim V as the information which is sent by the attacker. As like U. So, what happens? He is going to act as that X persons now. Okay, he's going to act as a replacing the X person, and he is trying to send all the information from the respective side. I'm going to get all the informations. Okay, so banking will be having such kind of a security system because many people are trying to do such a cases in the bank robberies cases also. Okay, so security system for the datagram is also very important. Okay, so security of IP datagram is nothing but we have to define what is the algorithm and the key. And we are going to do the packet encryption, packet decryptions, as well as the original authentication. All the things we have to do here. Okay. Here one of the examples have been given. An IP packet has arrived with the first value of 8 bits. Okay, like a 0, 1, 0, 0, 1, 0. So the receiver is going to discard this packet. Why this receiver is going to discard the incoming packet? What is the problem? Here we have the numbers now like a 0, 4 ones of 0, 4 times of zeros and 1 0. What is the problem with the packet and why the receiver have to discard here? Something is there. Let me find what is that. Okay. The error in this packet is nothing but there is an error in this packet. What is an error? The leftmost bits 0, 1, 0, 0 shows the version. So we are talking about the version 4. So what is the version 4 number is supposed to be? 0100. Yes, this is version 4. Okay, it is accepted. What is the next bit? 0010 I have. Because first 4 bit denotes the version. Second 4 bits denotes the header length. What is the header length supposed to be minimum value? 5. What is the value given here? 0010, which means 8421. Okay, 8421. So this nothing but value of 2. Yes or no? So the next 4 bits is about 0010 shows the header length with the value as a 2. So 2 into 4 I have the value as 8, which is not accepted for transmitting your data. What should be our minimum size? We should have the value as a 5. So that 5 into 4 we can have the value as a 20. So with this data, we cannot do the transmission from the sender to the receiver because we should have the header length, the minimum as a into 4. So in an IP packet, the value of your header length is something but 1000 in a binary. Okay, because what is the header length we can have? We can start with value of 5. So now this is accepted now. Now what they're asking, how many bytes of an options are being carried by these packets? You're asking how many options are being carried by these packets. Okay, so what is the length of the packets we have? Like a 32. So header field length is something but 8, which means the total number of the bytes in the header. Total bytes is how many total size we have? 4 bytes we have. So 8 into 4, or we can represent this in terms of 32 bytes. The first 20 bytes which are being occupied by the header. Yes or no? Header minimum size is nothing but 20, maximum is nothing but 60. Okay, so we have to start only with the minimum as a 20. So this is 32. Out of this 32 bytes, 20 bytes have been occupied for the main header. What is the remaining value? 12 values. This 12 value are given as the options. Okay. Right. Next is nothing but in an IP packet, the value of a header length is nothing but 5 to the base 16. Okay, or it has been mentioned in terms of the binary number. And the value of the total length is nothing but 0028. That's hexadecimal number, or in terms of binary number they are mentioned. Okay, how many bytes of a data are being carried by these packets? How many bytes of data are being carried by this packet? Let me see that. What is the header length? 010. So this is nothing but 4 plus 1 is nothing but 5. So the header value is nothing but 5, which means that the total length of the bytes in the header is nothing but 5 into 4. Yes, so 4 bytes we have, and given header is nothing but 5. So 5 into 4 is nothing but 20 bytes. Okay, done. And what is the total length of the field they are given? 28 is an hexadecimal value, and the binary value they are given like 40 bytes. That is the maximum value you can have. Yes. So which means the packet is carrying 20 bytes of data. Okay. So data length is equal to the total length minus header length. What is our total length we have? 40. Okay, this is 40 minus the header length is given by something but 20. So 20 is equal to, I'm going to have it as a 20. So 40 minus 20, I'll be having as a 20. So only header length uses, as we see like into 4, we're going to get the total lengths. Right. So how some may ask the question, how I got this value of 40 here? So this is all given this value here. This is nothing but 8 plus 2, 16, 16 value is nothing but 0, and next I have like a 32, so 32 plus 8 is nothing but 40. So that is I'm going to be have the total length. Okay, so total length is going to be 40, 40 minus this 5 into 4 is nothing but a 20, so 40 minus 20 is nothing but a 20. Okay, yes. So the IP packet has arrived with the first few hexadecimal digits as shown here. Okay, the IP packets have arrived with the first few hexadecimal digits as shown here. Okay, so they're given like a continuous values, and we have to find that hops. We have seen the packet time lifetime period. Yes. So how many hops can this packet travel before being dropped? As we see that dropping may take place at any time period depending upon the maximum given time period. So data belong to what upper layer protocol? Right. So here they've given us a break. Now before this only we're going to give a look. Okay. First, to find the time to live field, we should skip the 8 bytes. That is hexadecimal values, 16 hexadecimal values. Okay, so the given 4 bits is nothing but 1 bit of hexadecimal. So 4 bits is equal to 1 hexadecimal values, and 1 byte is equal to 8 bits. So in this 1 byte, I'm really having like a 2 hexadecimal values. So because in 1 byte, I'll be having 8 bits. So 4 plus 4. So I'll be having 2 hexadecimal value. Okay. The time to live field is going to be occupied in the 9th field. What they say they are using to skip the 8 bytes. Okay. So we are going to keep on skip like how many goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes or no? So 8 bytes or 16 hexadecimal value. We are going to skip all these values. So we have to see what is our 9th byte. What is the 9th byte? Here we have 0, 1. This is my 9th byte. So this is nothing but 1 byte. This is nothing but 2 byte. So like 2 bytes is equal to 1 hexadecimals. So this is nothing but now the 9th value is now 0, 1. This means that the packet can travel only 1 hop. So this 0, 1 stands for 1 hopping can take place. So the protocol field in the next byte is nothing but 0, 2. So this is the 9th byte, this is the next 10th byte we're going to have. So there in this location we have like a 0, 2, which means that the upper layer protocol is nothing but IG and P. So this 0, 1 stands for how many number of hops I'm going to take a place. And next is something but 0, 2. So what are the protocol we are going to use in the center side, which has been mentioned in the respective datagram. Okay, right. So as we already seen the checksum process, because checksum are supposed to be done in the center side, so that if any error happens in the data during a medium, which can be identified by the receiver, and we can able to correct the respective errors. So the center side we are going to divide all the data, and we're going to find what is the checksum, and all put together we have added in data, and with the original data we're going to make some complement. We're going to add all the data put together. The receiver is also we're going to do the reverse process. Right. So with this I'll stop.